thanks also to the organizer. It's a great honor to congratulate my PhD advisor once again to his 80th birthday from the stage. In 1992, Wolfgang organized a big conference in Münster, and I'm sorry that I missed that one. I was only an undergraduate student then, in his first year, attending the linear algebra course of Wolfgang. Perelman was there, Frommer was there. And one other thing that happened at that conference was that Carsten Grove proposed his so-called symmetry program. So Grove suggested, inspired by previous work of Xian Kleiner, classify manifolds with positive sectional curvature with sufficient symmetry. So this is a bit vague on purpose. I won't go through all of the history. Certainly a lot has been done, and I certainly was also inspired by it. And so the talk of today is also a little bit in this direction, although one has to be very generous about what classify means. But on the other hand, we are not too generous on what a lot of symmetry means, right? So we actually, it's a sort of a result where we assume relatively mild symmetry assumptions, but we can still do something. Okay, yeah, I will talk a bit about the history, but maybe I start by stating the main result. So suppose we have an even-dimensional manifold, and then an even-dimensional closed orientable manifold with positive sectional curvature. And assume the symmetry rank of M. So that's the rank of the isommetry group, right? So that's the rank of the isommetry group. The isommetry group is always a compact Lie group, and has a maximal torus, and that the dimension of the maximal torus is called the rank. So when we assume this is larger or equal than 3 times log 2n. So that's a logarithm with base 2. Okay, so then we can say a little bit about this manifold, right? So then there's a model. This n-dimensional model. Rank 1 symmetric spaces. So that the manifold shares some properties with this model. And so the main thing is, for us at least, that the Eulercharacteristic is the same. So the model manifold is also, you look at all rank 1 symmetric spaces, dimension n, there are not that many. So HBN, CBN for the sphere, simply connected. And then the Euler characteristic is the same. Moreover, yes, okay, should have. Let me put it here. So much space. Moreover, the rational homology of M is equal to the rational homology of the model well for I less than 2 times log to n. Right, so up to a certain dimension, the manifold has the same homology as, well, actually, homology groups, I should say. The ring structure, there's actually one addition. The groups are the same as in the model case for the ring structure. We cannot rule out the ring structure of S2 cross HBN. That would be allowed, but the groups are then the same as the groups for CBN, but the ring structure is different, right? So, but yeah, the ring will also be is very severely restricted, at least rationally. Okay. Yeah, maybe another slight remark that this might not be. I mean, or maybe you could hope for more, right? So another corollary, it's more a corollary of the proof. If the Eulercharacteristic is actually 2, then
equals 2.
Equals 2, yes. Then the manifold Mn is deconnected. H connected with H. Larger or equal than log 2 times log 2n. So in this case, it's not just rationally the same homology as the sphere, but integrally. Right? So if the Eulercharacteristic is 2, then actually also integrally we actually have the same homology in low degrees as we see on the sphere, right? Okay, so yeah, so I should say this is not all new. Part of it was known, right? So let me first say sort of directly to this. So Lee cannot, in his thesis, prove that at least 12 proves that the Euler-Characteristic at least is positive under these assumptions. And he also proved this 4-periodicity theorem, which I will later on come to, which is very important for the kind of proof, for this proof. And then there's work of Lee cannot with Bert Ammann. And they prove bounds on the Euler-Characteristic. Bounds on the Euler-Characteristic. I mean, not quite the optimal bounds, so the ones of symmetric spaces, but they do prove under these assumptions. I mean, certainly much better bounds than Gromov bounds. I mean, something a little bit more than linear rows with the dimension.
So this hypothesis is, of course, impossible in low dimensions. Where's the cutoff where it becomes possible?
Oh, well, you figured out.
Yeah.
Yeah, I mean, yeah, this is not interesting in low dimensions. Yeah, I will talk about other results, previous results, because I actually need some of the tools which were used there also afterwards. I mean, yeah, they are actually much better in low dimensions, right? But I guess if you if you are at 1 million, right, so then this is like log 2, and from 1 million is like, what is it, 20, so that's like 60, so you can, that's, degree 60 to 50 torus already sort of suffices to at least control the Eulercharacteristic. I mean, yeah, it's not so much, but at least something, right? I mean, you know something which you don't know otherwise. And of course, the symmetry program of Carson was sort of inspired by the fact that without symmetry, you basically don't know anything. I mean, well, that's not true, but you know very little about simply connected manifolds with positive sectional curvature. You know embarrassingly little. And in particular, you don't know really why there are relatively many examples with no negative sectional curvature, but very, very few examples with positive sectional curvature, right? So, I mean, there's a Betti number bound by Gromov, but that applies with sectional curvature bounds. All right, so, and if you have some symmetries, then you can all of a sudden say something. All right, so yeah, I mean, maybe I mentioned, so if let's assume E is the symmetry rank of the manifold. I mentioned some previous results now. N manifold. So if D is larger or equal than n over 2, then Robison proved that the manifold is actually, and let's assume also simply connected. For simplicity, actually, for this theorem, the classification is slow without assumption of being simply connected, but in this case, it's diffeomorphic to cross. And the way this theorem is proved is actually related to a theorem of Detlef Komol and Wolfgang Meyer. So mainly you first should use that this torus actually has a fixed point, or in even dimension has a fixed point, or in odd dimension has a circle orbit. So there's a large isotropic group, and then it's a simple linear algebra argument that tells you there's a circle which fixes something of codimension 2. You divide out the circle, you arrive at something which has boundary, still has positive curvature, and if you have boundary, it's similar to some manifold with boundary and positive sectional curvature. That's like a non-compact manifold with positive sectional curvature. That's contractible, right? So that's, and then you continue from there, right? So I mean, so it's to be, yeah, it's Alexander geometry to some degree, but actually on this level it's still pretty much just Riemann geometry, even on the orbit space. Okay, so yes, so there was a result. I'm not mentioning all results. There was a result with one degree less symmetry, but wrong. Where you also still get almost classification. I guess not diffeomorphic to cross, but homotopy equivalent. And then there's a result by myself from O3. So the degree of symmetry is like n over 4 plus 1. Then this implies that the manifold is homotopy equivalent, tangentially homotopy equivalent to a cross. So the Pontryagin classes are also the same as the one of the compact one-symmetric space. And here actually the HPN shows up, right? In this situation, it's only CPN. HPN actually doesn't have as much symmetry, but HPN actually does show up. And so one of the important tools that was used there, and which is also important here now, is the so-called connectedness lemma. And that's more theory on loop spaces in the proof. So if you are following the following situation, so you have a totally geodesic submanifold. It's totally geodesic. So we will always have a positive sectional. We will always assume that there's positive sectional curvature for the manifold, right? So now we have a totally geodesic submanifold closed of codimension k. Then the inclusion map into the big manifold is n minus 2k plus 1 connected. Okay, so that's part A. There's a second part, which is also somewhat important for what follows. So if we actually have two totally geodesic submanifolds, so then you can take the intersection of the two, that's also totally geodesic submanifold, and take the inclusion map into the smaller one. So let's assume K1 is smaller than K2. So we consider the inclusion map into N2 N minus K2. So that's N minus K1 minus K2. This inclusion map. Okay. Yes, now I should actually tell you what that means. That map is that highly connected. Okay, yeah, like so a space is H connected if all the homology groups or all the homotopy groups up to dimension H vanish. But a map is that highly connected if the map induces isomorphism in cohomology or on the homotopy groups up to that degree, right? In the degree itself, the map on homotopy level is only surjective, but below that it's an isomorphism. In the final degree, it's assumed to be at least still surjective. All right, and the important thing for the second one is that this is actually the expected value of the dimension, right? So the intersection here is transverse, right? So in the second situation, the intersection is transverse, then the inclusion map is as highly connected as the dimension of the submanifold. So that's a very particular case. So this intersection transverse. Then the inclusion map here is as highly connected as the dimension of this intersection, right? So the dimension and if the intersection is transverse is of course n minus k1 minus k2. And now you basically have two Poincare dualities, right? So you have the Poincare duality of the submanifold and you have the Poincare duality of this manifold. And now you can play with it. You basically combine them. And you see that this submanifold must have actually to the smaller one, K1, K1.
No.
Oh, no, yeah, it was the smaller one. No, the smaller one is K2. Sorry. Yeah, the codimension is bigger, so the manifold is smaller. Right. Right, so this will have a K1 periodic cohomology. Right, so this implies N2 has a K2 periodic. And yeah, and there now comes the result of we cannot what was it from the 4 years ago? So if okay, so I guess if K1 plus K2 is less than n over 2, then it follows that rationally you have 4 periodic. That's 4 periodic homology. So, and by periodic homology being, I mean there is an element in the, so K2 periodic homology being there's an element in the K2's homology such that coupling with it gives you an isomorphism in all degrees except possibly in the first degree and in the very last degree, but in all positive degrees where you could expect an isomorphism, you get an isomorphism. That's what it means, right? And whenever you have a K2 periodic homology ring, then rationally, automatically, you have actually a 4 periodic homology ring, right? So that's a clever application of Steenberg squares. All right, so that's sort of what gets us going from basically linear assumptions to logarithmic assumptions, and Lee Kennard and Bellarmine already did. Manuel. Did several results in this direction. Right. Okay. Yes. So now let me try to do a little bit of the idea of the proof. Okay, so yeah, what's again the situation? We have n manifold and the symmetry rank the manifold is larger than 3 times log to n. And okay, I will focus on the computer. How do you compute the Eulercharacteristic? Right. So yeah, we look at choose the maximum b such that the following holds. So choose the maximum b, and the b will automatically be larger than 16. Such that there's a fixed point component, there's a subtorus, there's a torus, E inside the isometry group, maybe not the maximal torus, fixing a d-dimensional component, EB. Such that so the dimension of the torus is big, but if the dimension of the fixed point set is big, then you actually award that a little bit. So when the right condition turns out to be this, minus 2 times log 2b.
So this BD is automatically a totally GDs that connect submanifolds, right?
Yes, right. I mean, so fixed, so the, yeah, I mean, all right, so, I mean, these theorems of totally geometric submanifolds are, of course, important because fixed point sets of isometries are going to be totally geometric submanifolds, right?
And they're connected because of the curvature condition.
No, they are not connected. Oh, okay. Fixing a component to, yeah, I mean, it's yeah, no. If they would be connected, then it would be computing the Eulercharacteristic would be easy because it's an easy result that the fixed point set of the Eulercharacteristic of the fixed point set of the torus is the same thing as the fixed point set of the manifold, right? So if it's connected, then you only need to compute this one. That's usually not the case. It's not going to be connected, but we look at one fixed point of the torus, and then always insist on that connected component if we pass to fixed point components usually. All right. So what does this mean? Right. So if you take a codimension 2 torus inside this torus, right? So a torus of dimension b minus 2, then the dimension of the fixed point set will be at most double, 2 times b, right? Because otherwise you would have found a larger fixed point component satisfying this condition, right? So this sort of means, and this is important to prove the following, which is sort of clearly related to the Euler characteristic, which proves very easy. So we now look at we don't look anymore at the maximal torus, we actually investigate the action of this subtorus, right? Okay, yeah, I should say why is the dimension, why is the B at least 16? If you want to pass to a subtorus fixing something 16-dimensional, then you have to pass at most to a subtorus of codimension 8, right? So the 2 logarithm of 16 is 4, right? So and then times 2 is also 8. Right, so you can actually do that, and originally you had a symmetry rank like this, right, and then you can pass to a subtorus, which has this property, right? Okay, so, all right, so step 1. Suppose prime is another fixed point component of the torus, different from B. Right, so then there's a subtorus that's unique of codimension 1. Such that E prime is contained in the identity. So both B and B prime are contained in the same connected component of this torus. Right, so we can find a codimension 1 torus so that they are both contained in it. Right, and then, okay, so what do we need to do? We need to compute the Euler characteristic of the fixed point set, and then we can sort of look at fixed point sets of codimension 1 torus, right? And yeah, so the torus is actually unique. That's also important for the law later on. Okay, so that's, as I say, the proof is easy. So choose a minimal fixed point component. So we take a submanifold of some dimension m inside m, and it's a fixed point component of some subgroup of H torus such that this is the case, right? So they do lie in the same connected component, in this component, right? And so now what do we need to prove? We need to prove that the torus acts only as a rank 1 torus, has the action of the torus, so plane. The action of the torus on this component as a kernel of 4-dimension 1 is highly ineffective, right? And then we pass to the action. We look at the kernel of the action, right? That's a 4-dimension 1 torus, and that then obviously satisfies at least the existence part, right? For the uniqueness, the argument is different. Okay, so that's what we need to prove, right? So that this thing has a big kernel, right? And okay, so I mean there's some sort of numerical computation involved, which I don't want to get into. Let me but I can make clear how the argument goes, right? Let's assume that the kernel has codimension 2 and try to get a contradiction, right? So suppose it has a 2-dimensional kernel. Suppose, I mean, this is only a special case, but this will sort of, the general proof works the same way, right? So suppose the kernel has codimension 2. Okay, so then what can I say? It doesn't seem like a lot. I can say a lot. Well, I can say something. I can say then that m is less than 2b. Right? So if I have a kernel of which has right, so if the kernel has codimension 2, right, then that means potentially when I choose my torus, this torus was also among them, right? So if actually the dimension would actually increase by factor 2, right? And I pass through this codimension 2 subtorus, then the symmetry degree would go down by 2. But in my formula, the b would increase by something more than at least by a factor 2, right? So this b would become a 2b, and I would get an extra 2 here also, right? And I did choose my b maximal, so that cannot be, right? So the dimension of my minimal component in this particular case is bounded by twice the dimension of my fixed point set. All right, so now I take 2 points, right? So 1 point in dB and 1 point in the other component. And these are fixed points. Yeah, well, actually by definition they are fixed points of my torus. Alright, so now I look at the representation in PP M plus PQF. And to be more precise, so this I intersect with PP with a possible complement of this. Right? I mean, I know that the torus, I look at the isotropy representation of the torus, right? So this fixes completely the b-dimensional component, which in this vector space now only makes at least 1/4 of the total dimension, right? It makes up at least 1/2 of n, and it makes up 1/4 of the total dimension. Alright, so now inside I have, there are two evolutions. There's an effective action of Z2 squared inside my maximal torus as isotropy representation. Right, so I do know that my torus still acts as a two-dimensional torus on my submanifold, right? So I can claim. So after I make the action effective, I can still find a sub-action of. I look at the evolutions, right? So there I can find a Z2 squared sub-action here. All right. Now I look at the evolution whose dimension inside this linear vector space has a maximal fixed point component, right? So the dimension is maximal, right? Okay, so the dimension of this here, the space here is at most, so the dimension is at most 3b. And of this vector space, because I pass to the dimension of m is less than 2b, and so this is at most b-dimensional, the first vector, and this second vector is at most 2b-dimensional, right? So and if I have two evolutions, then actually one which commute, right? Then it's easy to see that one of the evolutions fixes at most something, fixes at least something which has a third of the dimension of the vector space, right? So I mean, if I look at the evolution where the fixed point set is at least as big as possible, so I can find an evolution. There's an evolution fixing something b-dimensional. The dimension is bound by 3D, okay, so the dimension k over. I mean, 2m minus b over 3-dimensional. Okay, and now if I look now at the fixed point set inside here, right? So if I down pass to the orthogonal complement, I actually see that the fixed point set of this evolution makes up more than half of the dimension of the vector space, right? And that's sort of a standard trick, which implies by Sunch, right? So that means the dimension of the fixed point component at P and the fixed point component of Q add up to something which is larger than the total dimension of the space. But then there's a result of Sunch. So if you have two totally geodesic submanifolds, which whose dimension add up to something which is at least equal to the dimension of the manifold, then they have to intersect, and that means the components are actually the same, right? So actually this involution will actually fix something. It will, P and Q will be the same component of this involution, right? And that's a contradiction to the minimal choice of my component here, right? And the general argument is completely analogous, right? I mean, it's only particularly easy in this case. Maybe it's not so easy that you understood every single detail, but it is very simple application of Synch theorem. All right. Okay. Other question? All right. So now. Okay. All right. So now. Step 2. I mean, consider all coordination 1 to array. Subtorah fixing something larger than okay, larger than my original component, right? And so how do I get them? These subtori. I look at the isotropy representation of my torus. That sort of splits in two-dimensional representations, and for each two-dimensional, I mean, on the tangent space of PB, of course, the representation is trivial. I don't have to do anything there. I look at the normal bundle, and there it splits into two-dimensional non-trivial representations, and I look at the identity component of the kernel, right? So I look at all these possible kernels that occur there, and then I have my Torah, right? So it's easy to figure out what these tori are. Right, so then of course now, I forgot to say the unique, maybe I should come back to that. So then the Euler characteristic of the manifold is equal to the Euler characteristic of PB plus some I1 to 1 to k, Euler characteristic of fixed point set, m t d minus 1 I. Okay, so that's supposed to be the fixed point set, and I take the component that contains the d. Okay, and then minus the Euler characteristic again of this sum. Right, so this is immediate from I mean, this is actually doesn't have to do anything. Right, so the Euler characteristic of the manifold is equal to the Euler characteristic of the fixed point set, and the same goes for this fixed point component, right? So the Euler characteristic of this fixed point component is equal to the Euler characteristic of the fixed point components of the whole torus, which are contained inside the submanifold, right? One submanifold which is always contained in it is this e-dimensional submanifold, right? And then there might be other components, right? And so, and step one ensures that I actually, because of the existence part, in the sum, I count in this every other component, right? So the difference between these two is exactly the Euler characteristic of the fixed components of TD, different from the submanifold B, which are contained in this fixed point component, right? And I get them all, right? That's what step one says. I get them all, right? So that's what the formula says. Okay, and because it's unique, I actually only count them exactly once, right? And okay, so the uniqueness, I forgot to say, is a corollary of the connectedness lemma, right? So if I actually have two, in the theorem, if I have two codimension 1 subtori containing the same component, then I look at the codimension 2 subtori, whose fixed point component is at most, the dimension is at most 2b, right? And then the other two components intersect in something which makes up more than half of the dimension, and then the intersection is actually connected by the connectedness lemma, right? And that contradicts, that's why it must be unique, right? So you get an immediately contradiction to the connectedness lemma. It's not unique. All right. Okay, so that's a nice formula, but as long as you cannot compute these things, that doesn't really help you. I mean, one thing which you can actually compute is the different dimensions of these components, right? So, certainly the dimension n is equal to b plus some I1s from 1 to k, and now I take the dimension, the difference of the dimensions. Minus b. Right, so that's basically just how I get all these tori, right? So how do I get the tori? I look at the isotropy representation in the normal bundle, look at the irreducible representations. Some of the irreducible representations might have the same kernel, right? Then the dimension actually goes not just up by 2, but by 4 or 8. But every single isotropy representation has one kernel, right? And it's counted exactly once. That's why I have this formula, right? And of course, the idea is that somehow I want to have a formula for these components so that I get a consistent formula for the Eulercharacteristic, right? So that's basically the strategy. All right, so now how do we do that? Okay, yeah, you're right, yeah, there's one more important step before, which is also very simple. The inclusion map, so for any h, for any subgroup h inside the torus, the inclusion map of PB inside the fixed point component of the subgroup is, and h, in particular h would be just the trivial group, right? The fixed point set is of course everything, is 2b over 3 connected. So that means this submanifold, I mean, it's at least 60-dimensional, right? So the first cohomology groups of any fixed point component of this torus, I mean, they are always the same, right? So, and in particular, somehow these things cannot be modeled on different Riemann symmetric spaces, right? It cannot be that one component actually has the cohomology of CPN and another component has the cohomology of HPN, right? Because for all of them, this inclusion map is 2b over 3 connected, and that also includes the inclusion map into the manifold, right? So that means up to dimension 2b over 3, they all have the same homology. All right, so that theorem is again easy to prove. I mean, relatively speaking, it's just some linear algebra, because if you have a fixed point component and the dimension is big compared to b, then automatically you do have some symmetry, right? So because the torus cannot act with a large kernel, right? So for example, if the symmetry degree is at most 2, right, of this component, right? So if the torus act only with a two-dimensional as a two-dimensional torus on this subcomponent, right, then automatically the dimension can only increase by a factor 2, and that helps you to find submanifolds of sufficiently small codimensions so that the inclusion map is highly connected, right? So that's basically the idea. Okay. All right. So now, yeah. So step 4. Step 4 is now that these guys are all these submanifolds are all for periodic homology. Yes, rationally. For periodic. Right, okay, so that means automatically that the fourth Petty number is already at most 1. And okay, so then, yeah, step 5 is basically already the end. The third Petty number of our manifold is 0. So of course the first Petty number is 0. If the third Petty number is 0, then all the odd homology groups of the submanifolds vanish. And so the second Petty number, right, depends on the parity of the dimension, right? So if you are in dimension 4 for n plus 2, then the second Petty number is equal to the first Petty number by cogradiality. And if you are in dimension 4n, then basically, also by cogradiality, you can sort of basically generate the element in degree 4 by elements in degree 2, and that means you actually have a 2 periodic homology ring, and then you are happy too, right? So then things are even better, right? So that then, if you know, but this was already known by Manuel and Lee already did this. Right? So once you know that the third Petty number is 0 and you have such a fixed point component of a sufficiently large torus, then the homology ring is like it's a homology ring of a rank 1 symmetric space or S2 cross HPX, at least rationally. Okay, so I'm probably I'm already almost out of time. Yeah, maybe. I mean, this 4 periodic homology, you basically bring yourself into a situation where you sort of have 2 submanifolds intersecting at some point transversally, and then you apply the periodicity theorem of Lie, right? So, okay, so let me get to why is the third Petty number 0? Okay, well, yeah, I can only sketch it. It might be a bit difficult. So, but the basic situation is like this. Suppose you have, let's just look at the following case. You have 2 torus fixing something, and inside you have 2 with ones. And so that the fixed point set intersect transversally. And the fixed point set of 2 torus. And let's assume that the codimensions are small, right? So the codimension is less than n over 4. Right? So this, in reality, this will take place in some totally geodesic submanifolds. This will not take place in the manifold itself. You can usually not expect to get in the manifold itself something which has codimension less than n over 4. All right, so yes, so then right, so then you basically know that the cohomology ring of the whole manifold, I mean, it's one of the submanifolds has a 4-periodic cohomology ring, but then the whole manifold also has a 4-periodic cohomology ring. And so this implies Mn has 4-periodic cohomology, rational homology. And now you use equivalent homology, right? So you actually also know that the subtorus, or yeah, you can actually stick with the action of this as one, right? So this fixes something which has whose inclusion map is basically as highly connected as a submanifold, right? And now so if you look at the spectral sequence for equivalent cohomology, that kind of tells you that the equivalent cohomology surjects back onto the fiber of the submanifold, right? Just because the action is actually driven here on the submanifold, right? But since the submanifold is so highly connected in the manifold, that also means that the spectral sequence for the whole manifold, for the S1 action on the whole manifold, degenerates. And then there's a theorem of Besson telling you if the whole spectral sequence degenerates, then actually you have equality in one of these inequalities, namely that the total Betti number of the fixed point set is equal to the total Betti number of the manifold, right? And so if we were to have 3 rational, if the third homotopy group would not be 0, then we would actually see it in some other fixed point component also. And this doesn't go well together, right? So then you actually do again an argument with Eulercharacteristic, and you basically see that if you actually have 4 periodic homology and you have third Betti number is even, second Betti number is at most 1, fourth Betti number is at most 1. So basically the Euler-characteristic is at most 2, and so that doesn't go well together, and you can actually rule it out. Okay, yes, thanks.
Questions or remarks?
So this is in a range of dimensions where if the dimension is odd, you really can't use nothing but other than
that's true, right? So that's probably you can say something on circle orbit. There should be at least a formula estimating the circle orbit, but I'm not so sure. Yeah, that's a bit strange that you cannot do equally well in odd dimensions. I mean, it would be actually good if you could do it also in odd dimensions, even so. Yeah, it would probably also mean that even dimensions you can also do things integrally than in low degrees, because you can always, for example, the CPN model case, you can pass through this S1 bundle over the even dimensional manifold that doesn't have positive curvature, but it kind of has enough positive curvature so that most arguments go through. And you can argue then, if you can say something there that maybe fixed point sets are always connected or so, then it would actually do something, right? Well,
Other questions? Or?